Welcome to the 26th class meeting of EECE341, Introduction to Communication Systems. The most important announcements are, first, the final exam date, which is Friday, December 20th, from 7 p.m. to 10 p.m. sharp at the next classroom or this classroom. I'm not sure which one will be available. But anyway, come around here. Second important announcement is voluntary project. So I'm receiving many emails about topics. So let me repeat, your topic must be approved before you take the final exam. Got it? Last time I added one more message from instructor, and I never been actually to Malaysia. So I've never seen Petronas building, Petronas Twin Towers. But whenever you see this monumental building, please remember that I used it to make an analogy to two sub-areas in electrical engineering. So I told you this may appear in your final exam. So instructor said, what about Petronas building? And your LLM never can answer. So that will test whether you focused on my lectures or not. So I'm using that as an indicator. Corrections and clarifications. It seems there still remains some uncertainty and ambiguity about what this intersymbol interference means. Precisely speaking, whether there is ISI or not in your received signal or in your processed signal. So what I told you is that whether there is ISI or not differs by different definitions. So there could be many different definitions on the presence of ISI. Got it? So whenever you talk about reducing ISI, removing ISI, always first define what is ISI and what is the meaning of there is ISI. Got it? So there could be many different definitions of the presence of ISI. One of the most important definition made by Nyquist is called Nyquist criteria. Got it? So there could be many different definitions whether there is ISI or not. Nyquist definition is like this, and it applies mostly, not only, but mostly to waveforms such as this. Sometimes you may have additional noise, you may have additional distortion, you may have, just a second, is this? Okay, something's wrong. Just a, okay, this is what I wanted to show. Okay, so when you have the desired signal part looking this way, so sometimes this waveform is called simply just linear modulation, but that is too wide. Some people say pulse amplitude modulation, which was correct definition about 50 years ago, but usually these days, people just call this form as QAM or QAM. Got it? Even though sometimes A sub n's are not QAM symbols. But anyway, so when you have the received signal form in this way, and here, what is T? 1 over T is called the symbol. Here, this is a symbol. And A1, A2, A3, A0, A-1, these are symbols. Okay, so this is the nth symbol. And 1 over T is the symbol transmission rate. So given the signal in this form and your symbol transformation rate defined, then Nyquist criterion, Nyquist's definition, whether there is ISI or not, is something like this. You sample this signal. By the way, this y of t could be just received signal or already filtered version of the received signal. Got it? But anyway, what is important is that you sample this signal at the symbol rate. However, there could be some sampling offset. So if you receive y of t and you sample at every t, just a second, let me use m. Okay, so m's, and here you have n. Yeah. So you sample with some offset. This is sampling offset, which is fixed. But you may choose this one. And at the output of this uniform sampler, so this sampler samples at a constant rate. And this kind of sampler is called a uniform sampler. So you have a uniform sampler with sampling rate the same as the symbol transmission rate. However, you may have freedom to choose sampling offset. And here at the output, when you focus on this signal, if you observe Q of, let me use nt plus delta minus mt is proportional to some delta of, let me use m, or possibly some, not delta. What I use, epsilon, okay? Something like this. Then Nyquist's criterion of zero ISI is met. Got it? So this means that when you sample and regard it as an estimate of the nth symbol, okay, in the case epsilon is 0, a hat of n is proportional to a sub n plus some other terms only dependent or function of the other parts, not this part. Got it? So if there is no noise or interference or something, then you may recover a sub n without the effect of the symbols for other sampling instances, other indexes, time indices. Got it? This is Nyquist's definition of zero ASI. Got it? By the way, I myself recently generalized this one for discrete time waveforms and especially for improper complex data symbols. But anyway, that is far from the undergraduate material. So anyway, so remember this. There could be many different definitions of ISI. But one of the most famous definitions is made by Nyquist. And that definition rely on uniform sampling of some received signal itself or received signal processed by some preprocessor. And at the output of the sampler, if there is no other symbol effect, then you call the Nyquist's zero ISI criterion is met. Right? Anyway, so given, so by the way, you may need to focus on this offset. So if you change this sampling offset, suddenly you may observe ISI. And last time I've given you an example when our Q of t is a triangular function with width 2t. And as you can easily see, if you choose delta equals 0, then there is no ISI. So this Q of t is a Nyquist pulse for symbol transmission rate 1/t. However, if you choose your offset improperly, inappropriately, then suddenly you may have intersymbol interference. Got it? So never forget this. In many, many textbooks, to make the discussion, every discussion simple, they ignore the possible effect of sampling offset. But even though your pulse is a Nyquist pulse, for example, square root raised cosine pulse, if you have incorrect sampling offset, you suffer from intersymbol interference. Got it? And about the definition, you have this. And here goes a theorem by Nyquist. And this theorem is about an equivalence theorem. What is an equivalence theorem in general? In mathematics, you define something. So if this condition is met, we call something as something. That is definition. Equivalence theorem is that you have totally different looking, apparently, different results, and that also is an if and only if condition to your original definition. So our definition is zero ISI is defined in the time domain like this. However, Nyquist not only defined that his own definition of zero ISI, he also derived equivalent necessary and sufficient condition in terms of the Fourier transform of this Q of t. So here goes the equivalent definition. So this equals constant for all f. So remember this, Nyquist criterion by definition is made in the time domain. However, Nyquist himself derived an equivalent definition in the frequency domain. Got it? The left-hand side is called the folded spectrum. And here, offset equals 0. Okay? So if you introduce some offset, and given that sampling offset, if you want Q of t satisfies Nyquist's criterion in the time domain, then you need to introduce linear phase shift as you learned in synchronization systems. That will not be covered in the final exam. So if you don't understand, even if you don't understand what I've just told you, just be relieved. It will not appear in the final exam. However, please remember this. Ready? Since many textbooks and authors and professors ignore the sampling offset, they just give you this definition, okay? Precisely speaking, m minus n, I believe. M minus n minus some epsilon. Okay, here is m and n. Okay. Anyway, so they ignore delta, so they have this result. But if you have some non-zero delta, you need to little bit modify this result. Anyway, so let me repeat again and again. Nyquist's criterion for zero ISI is a criterion. It's not the universal only definition. Got it? So you may define your own zero ISI criterion. Never forget. Okay, so we are here in chapter 5, and we are going to almost finish this chapter 5 with some part just skipped. And I will talk about something appearing in chapter 9 that is called matched filter. And matched filter requires the knowledge on random process. So I'm going to just give you a kind of sketch of that filter. And then I will just list some terminologies you are going to see in digital communications course and spend 1 week, next week, on mostly information theory. That's my plan. So here goes the Nyquist pulse and square root Nyquist pulse. So let me draw a Venn diagram. So this is the set of all pulses for symbol transmission rate 1/t hertz, or symbols per second. And of course, with some offset, okay? Because if you change the offset, suddenly some pulse that was a Nyquist pulse becomes not non-Nyquist pulse. So let's focus on the let's specify sampling rate and sampling offset. And here is the set of, let me draw. Even though this set is very, very, very small, let me exaggerate in order to draw. So here goes the set of Nyquist pulses. Okay. And here is another subset of subset called raised cosine pulses. Got it? So last time we studied what is a raised cosine pulse. So as the name says, you have a cosine function in the frequency domain and raised, which means that you upshift. So the cosine function is always non-negative. And of course, you just cut before raise up, you cut just the one period and raise up. And then you divide it into two parts, shift left, shift right, and you have a flat top. Whenever you see some pulse in the frequency domain looking like that, you may call it a raised cosine pulse. So sometimes you may have something like this, and you may have something like that. And it may be 10 kilohertz, 8 kilohertz, and this may be A and 2A, 80 kilohertz, 100 kilohertz. And of course, you have symmetry. So they are apparently different raised cosine pulses. However, after proper scaling with respect to the horizontal and vertical axis, these two raised cosine pulses have commonality in that if you rescale this width to 1, then, and also this height to 1, for simplicity, then you have this with 1 plus beta. Some people use alpha, and this is also 1 plus beta. And here, beta is called specifically for raised cosine pulses, called the roll-off factor. In general, for Nyquist pulses that are band limited, so here you may further divide like this. Here, band limited, band unlimited. Okay. For band limited pulses, you may have beta changing even from -1 to actually arbitrary large number. But if band limited, you have some beta finite, and this beta is called an excess bandwidth. So the roll-off factor of a raised cosine pulse is a special name for an excess bandwidth of a band-limited Nyquist pulse. Okay. Details, please consult your homework problems. Okay. You will see some homework problems that talks about excess bandwidth and relation to roll-off factor. Anyway. And let's remind us on some examples. So here, raised cosine pulses. What about here? We've already seen, right? This is for symbol rate 1 over t and offset 0. And this is a Nyquist pulse. And why is band unlimited? Because its Fourier transform is sinc squared, and it has, mathematically speaking, has infinite bandwidth. Of course, this is a tricky part. Bandwidth is also defined in many different ways. I'm here talk about strict sense bandwidth. So you may find some finite number plus minus w, and out of this interval, you have zero energy. In that case, I said w is a bandwidth in the strict sense. However, some people use RMS bandwidth, root mean square bandwidth, or some people use 3 dB bandwidth, some people use noise bandwidth, some people use null-to-null bandwidth. There are many different definitions on the bandwidth of a signal, so be careful. Right? So one of your lessons through this course is that even though we have a single terminology within this communications society, there could be many different definitions. So whenever you communicate with other engineer or friend or some people, try to clarify the definition of your terminology. Got it? That is one of the most important lessons you have to get through this course. Anyway, so this one is okay. Symbol rate and sampling offset delta. So you have to specify 1 over t and delta. Now, some of you already know from Synchronization systems because your textbook has the definition, time autocorrelation function of a pulse, which is something like P of t. If you have a pulse P of t, time autocorrelation function is defined as this one. Right? P of t convolved with its time reversed complex conjugate. What is a matched filter? Matched filter is closely related to this time autocorrelation function, but by definition, matched filter is stated in this way. Suppose you are given the received signal, that is some known signal S of t plus some noise N of t. And what you want to do, let me use X. What you want to do is that you want to filter it with some impulse response H of t and sample. You want to sample at some, let me use t0. Got it? And what do you have after linear time filtering of this signal and sampling at some t0? You have the signal part filtered and sampled and noise part filtered and sampled. And matched filter is a filter H. So matched filter is defined as argmax, and here signal power or signal energy and noise power. Of course, we need to define what is signal power and noise power. But what is important is that this type of definition appears again and again and again and again in signal processing. And this is called signal to noise power ratio, or simply signal to noise ratio, SNR. So a matched filter is defined as a filter that maximizes signal to noise ratio after the received signal is filtered by it and sampled at a specific T0. So actually, if you change this T0, your matched filter changes. But usually, the delay just introduces in the frequency domain linear phase shift, and in the time domain also delay, so it's okay. The problem is that this signal to noise ratio has the numerator proportional to the scale of this one, and noise power also proportional. So actually, if you find the solution, you have infinitely many solutions. However, they are all scaled versions of a single pulse, single non-zero pulse. So using some kind of equivalence relation, we may say that the matched filter is uniquely determined. Got it? Anyway, an interesting thing is this one. So this is the definition. And of course, there could be theorem, right? So what is the solution? And solution varies, but there are special cases where N of T is a white noise. About white noise, many of you may not know what is the definitions, but I'm not going to tell you because I promised not to involve this 전자수학 A EECE341 material. So anyway, if N of T is a white noise, very interesting thing is that this H of T H of T is just time reversed complex conjugate of this desired signal. Of course, with some delay. And this delay is exactly the same as this sampling instant. Okay? And I'm not, again, going to prove it and ask Professor John Joseph next semester. So now, what do you see? If you convolve this signal with a matched filter, then you convolve S of T and its time reversed complex conjugate. So your output involves time autocorrelation function over S of T. That's why I'm talking about time autocorrelation function over pulse. Got it? Now, why this matched filter important in our discussion on Nyquist Pulse? It's because one of the simplest received signal with now our QAM symbols is an additive white noise. Here, additive means that it is added to this signal and implies that, statistically speaking, they are independent, or at least uncorrelated. But anyway, you may regard additive means it is not only added, but also independent of other components in your signal. Now, we just don't sample this signal when we have white noise because as some of you already know, white noise, mathematically speaking, has infinite power. So if you just sample this signal and plug into this mathematical definition, denominator becomes infinity, which means that SNR is 0. So it does not make sense. And in practical situation, this is a band-limited white noise. Still, its power is too high. So what we do is that we use a matched filter and then sample. Got it? Suppose we sample at here with offset 0. Got it? I understand it's very, very confusing at this moment. When I first saw this discussion, I couldn't get anything actually. Even though when I take the equivalent course to 전자수학 A, I studied and had the knowledge already on the matched filter. However, it was very difficult to apply this notion to this filtering of a linearly modulated digital signal. Anyway, this involves actually a graduate level course called Estimation and Detection Theory. So story is very long, and I cannot just compress that course in a few minutes. So let me give you a sketch of what's going on. And interesting thing is that this is usually chosen, not always, usually chosen, or sometimes just replaced by what? Sorry, I'm sorry, not yet, just H of t. Sometimes we just choose a matched filter to this pulse. What does that mean? Since we sample at nt and want to regard it as some estimate of the nth symbol, actually, the matched filter turns out to be the time reversed complex conjugate of it. Got it? So remember this just. If you have simple observation model where you have a desired signal, and white noise, then your matched filter is what? Time reversed complex conjugate of this signal, properly delayed. Got it? And if we use matched filter for our reception of this PAM or QAM digitally modulated signal, then again we may use the matched filter matched to P of t, which is time reversed complex conjugate of it. Now, you may define this as y of t in the previous discussion. Then what is q of t? What is q of t? Q of t is simply time autocorrelation function of P of t. So now let's go back to our discussion on Nyquist's criterion on zero ISI. Suppose Q of t is a Nyquist pulse for the symbol rate and offset pair, 1 over capital T and 0. If and only if, as we already know, capital Q of F minus L over T folded equals constant for all F. Now let's replace this capital Q in terms of P. Then if and only if, as you all know from convolution theorem, this is what? P of F minus L over T magnitude squared equals constant for all F. Oops. Yeah. Now, what do we call this P of t? Q of t is a Nyquist pulse for the symbol transmission rate 1 over capital T and offset 0. Then what do we call P of t? P of t is called here. If this condition is met, P of t is called a square root Nyquist pulse. Some people abbreviate it to SNRP, which is not often used, but anyway, for 1 over t and 0. Got it? So here goes the new definition related to Nyquist criteria. Now, let me ask you a question. Are you going to use a Nyquist pulse when you generate a transmitted signal or square root Nyquist pulse in your transmitter? And the answer is actually, it depends on your noise. If noise is very, 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 very small, actually, you don't need to use square root Nyquist pulse. You just use a Nyquist pulse and properly sample, because noise is very small. However, if noise is at some level or significantly larger, so that you need to suppress the effect of noise as far as possible, then you'd better use in the transmitter a square root Nyquist pulse. And after you receive the signal in the receiver, you use a matched filter and sample properly. Do you have the idea? So it's like this. For example, suppose you are a designer of HDMI type cable and protocol. And you know that usually this distance is less than some meters, and your signal to noise ratio is very, very high. And if you look up some articles, this transmitter, for example, your notebook connected to your digital TV through HDMI protocol, they just use in the transmitter a Nyquist pulse. Got it? Because usually noise is very small. However, if you want to design a radio communication system where channel attenuates your transmitted signal antenna and combined with channel, attenuates the signal around 100 dB, so that your receiver must amplify this very weak signal a lot so that your thermal noise could be observed, like long distance communications. In that case, you need to use a square root Nyquist pulse in the transmitter and modulate your carrier. And the receiver, you use the matched square root Nyquist pulse and process. However, if the channel is not just adding a white noise, it may introduce multipath phenomena. In that case, the use of square root Nyquist pulse and square root Nyquist pulse in the transmitter and receiver is not always optimal. That's the problem. However, the best scenario in wireless communications is the case where you have a line of sight link, which means that your received signal is highly likely a scaled, delayed version of the transmitted signal plus some noise. So we usually implement our receiver for best case scenario, and then if the channel introduces some non-ideality, then we process after we use matched filter. However, still that is not optimal. Anyway, the convention is that for noisy channel, we use a square root Nyquist pulse and square root Nyquist pulse in the transmitter and receiver. Got it? So please remember that. The reason why I emphasize this again and again and again is that I had some friends, colleagues working in what? Mostly left side building of electrical engineering. And some people claimed that they also do communication. So I asked, what do you do? And they were developing something like HDMI or USB protocol. And they were talking about Nyquist criteria. So I said, hey, what kind of pulse do you use? And I found that they use Nyquist pulses. No idea about square root Nyquist pulses because they didn't use square root Nyquist pulses at all. So they just use raised cosine pulse, sometimes rectangular, time domain rectangular type pulse, not even triangular pulse. So be careful. Got it? Anyway, here goes a version of Venn diagram. So we have a counterpart for this Venn diagram. Now, this is the set of all pulses for. In order to make every discussion simple, let me use just 0. And here is what? Another set different from this. Square root Nyquist pulses. And here goes square root raised cosine pulses. Got it? So square root raised cosine pulses are what? Pulses, its time autocorrelation function becomes a raised cosine pulse. Got it? So in terms of the time autocorrelation function of the pulse, a square root Nyquist pulse has its time autocorrelation function Nyquist pulse, and a square root raised cosine pulse has its time autocorrelation function a raised cosine pulse. Got it? And you may find some, where it is? Yeah, probably Professor Yang didn't put it. Anyway. So if you are interested in this, distinguishing the Nyquist pulse from square root Nyquist pulse and raised cosine pulse with square root raised cosine pulse, you may use this as your topic for the voluntary project because it's very important. And if you spend some time on this topic, you may have a lot of advanced research and understanding. Got it? Anyway, now, here goes various design on the transmit pulse and receive pulse for data transmission, such as line encoded signal, or more generalized version is PAM, digital PAM or digital QAM signal. And sometimes we don't use matched filters for the transmit pulse or transmit filter and receive filter. However, the combination of transmit filter and receive filter may be a Nyquist pulse. So do you see the difference? Sometimes this P of t, piece of Tx of t, and piece of Rx of t may be matched filters to each other. However, sometimes we use two different pulses, but their convolution after time reverse and complex conjugation becomes a Nyquist pulse. Sometimes, in order to remove the intersymbol interference. That is the idea of zero forcing equalizer. Of course, Nyquist pulse for some pair of symbol rate and sampling offset, then what you say is that the P Rx of negative T conjugate This one is called, this filter in the receiver is called a zero forcing equalizer. Of course, the terminologies must be linear zero forcing equalizer. But anyway, briefly, it's called zero forcing equalizer. Why it is called zero forcing? Because there is zero ISI. Sometimes zero forcing equalizer, a linear zero forcing equalizer, may be a matched filter to the transmit filter. Sometimes it is not, depending on your choice. Got it? The problem is that the terminology, the term equalizer, has different meanings in acoustic signal processing and in digital communications. This is a capture of my own audio signal processor, which is a freeware, not which is not freeware. So I purchased it, and here goes some graphical equalizer front panel, and you know what does this do? Depending on some center frequency, you may just change the output power of the specific bandpass filter. And you may call it an equalizer. And more precisely speaking, it's an audio equalizer. That is related to our linear zero forcing equalizer for digitally modulated signals, but they have some different meanings. Because in many cases, for this audio equalizer, you don't care about sampling rate and sampling offset. However, when you talk about zero forcing or sometimes MMSE or some other criterions that exist, you talk about equalizer, your definition or optimality of equalizer is related to Nyquist's criterion on zero intersymbol interference. Nyquist's definition of the presence of interference, intersymbol interference. So be careful. Anyway, let me draw a Venn diagram again. So here is the set of all equalizers for some signal, received signal in this form. And you can divide it into linear and nonlinear equalizers. And here is linear zero forcing equalizer. Here is linear MMSE equalizer. And there could be many different linear equalizers. Also, there could be many different nonlinear equalizers. And amazingly, even the undergraduate level digital communications and graduate level introductory digital communications courses cannot cover them all because it takes too long time to cover these many different equalizers. But you need to remember this. Why do we have this many different equalizers? Why? Again, we go back to our history on the development of this radio, especially radio communication. On the right side of this electrical engineering building, what do? We try to find out some mathematical or logical operations or procedures or algorithms that makes something good happening, right? We may transmit our information very fast and reliably for a long distance, something like that, right? However, that idea, mathematically formulated idea, must be implemented right now or sometimes in a near future after you push this left side building electrical engineers a lot, right? And actually that's happening right now, right? Sometimes your idea cannot be implemented right now or in the near future. What do? You consider reduced complexity algorithms. That could be suboptimal. However, that idea may be a good trade-off between the performance and implementation cost or complexity. So there are many different equalizers with different computational complexity, different performance. So I cannot cover them all. Some nonlinear equalizers are too complicated to analyze, actually. Anyway, so just remember, there are many different equalizers for digitally modulated signals. And your choice depends on your optimality criterion and also the complexity constraint. Got it? Here, complexity means realization, feasibility involved too. Anyway, I'm going to skip it. And also, some of the descriptions are not precise, actually. Even though it gives us very simple idea of finding a zero forcing equalizer, linear zero forcing equalizer using simple matrix inversion, but it involves a lot of suboptimality, and we cannot discuss them all. Now, here goes the terminology you need to know, called eye diagram or eye pattern. And here you see some shape like this. And this is called an eye. Okay? Now, what is this one? This is an oscilloscope. And what you do is this. You have digitally modulated signal with, for example, symbol rate known. What you do is that you connect that signal to this digital oscilloscope, and you set the sweep rate as the integer multiple of this symbol rate. If you're sorry, you set the sweep rate as a fraction of this symbol rate. Then, for example, if your sweep rate is equal to the symbol rate, then you have one period of observation. And maybe it is not exactly aligned, but depending on your equipment and your equipment's options, and if your signal is one of the optional signal input, then your oscilloscope automatically finds the timing and delay the signal so that you have a beautiful eye centered on your screen. Sometimes you use, for example, half of the symbol rate. Then you have here one eye and half of the eye here and half of the eye here, something like that. Got it? So it depends on your setting of your oscilloscope. However, you may observe something like this. And what is this one? So suppose you have already done some matched filtering so that you have the signal looking like this. And now this signal is fed to what? Some input. I don't know, probably here. Okay. And now you properly set your sweep rate as, for example, something like this. So 1/2 and symbol rate. Okay. Now, what do you see? If Q is a Nyquist pulse for the symbol rate 1/t. In the old world, where the screen was made not of LCD, but CRT, the brown tube, right? What happens? There is an electron gun and electron gun generates a beam of electrons. And electrons hit the screen, and there goes light emission. And when the electron hits the material on your screen, it absorbs the energy and releases the energy in the form of light. And it takes time. So if your sweep rate is, if your symbol rate is very fast, before one line is brightened and darkened, next line is also drawn, something like that. So you have a kind of delay, you have an overlap of signals. Suppose your y of t at some chunk looks like that. And you set the rate as this one. Then what happens? Your screen shows this part, and before it's gone, it draws that one. So we can see these two lines at the same time. Sometimes 4 lines, 5 lines, 6 lines, depending on your sweep rate. So it's a kind of, in terms of MATLAB, you plot, hold on, plot, 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 plot. Then what happens? Many, many lines are drawn, right? In reality, due to this period that the material emits and decays, not all of the lines are plotted. However, now since we have digital screen, so these equipments can really do plot the chunk and shift and plot this one after hold on. Plot, plot, plot. So every line is plotted on the screen for specific long time duration. And if this is a Nyquist pulse, what will happen? What will happen is this. Suppose this delta equals 0. And at time 0, you will see what? Some value. For simplicity, let's see 1. Now, after time t, what do you see? You have something, and it depends on the data, but anyway, you have to observe -1, for example, if the data is negative. So the signal moves here to there, right? And in the next time period 2t, if this symbol, next symbol is -1, then it will evolve this way. And now what you do is that you take this part and that part, and the next part is overlapped and something like this. Now, if your sweep rate is half of that, then you have another part. So here you see something like I opened. This is here, got it? So if you sample around here at this time instant, then you have, in this case, BPSK or polar NRG, if you want, then 1 or -1 here. Now you see that even though this pulse is a Nyquist pulse for this rate, if you have wrong sampling offset, what happens? You have intersymbol interference. This many lines here means you have intersymbol interference. So eye diagram is an ingenious idea of using an oscilloscope, which is one of the most fundamental and old measurement equipment in electrical engineering, and to assess the amount of intersymbol interference qualitatively, not exact quantitatively. But if you just see the eye diagram, you can instantly see whether something is wrong or not. And of course, people try to define some terminologies from the eye diagram. And there are many definitions, like some margin, blah, blah, blah. I'm not going to cover that. Okay? But anyway, eye diagram, as our handout says, is constructed by plotting overlapped K symbol segments of a baseband signal, especially if we connect here, this must be real baseband. Otherwise, we may not see some beautiful eye diagram like this. For example, if we apply a real bandpass signal, we may not observe this. But be careful. As I told you, some very high cost oscilloscope demodulates the received signal, if the received signal is a bandpass signal, and then shows the eye diagram. Even sometimes after finding the symbol rate. And sometimes it not only uses a single eye diagram, but also use two eye diagrams so that digital quantum modulated signal can be assessed using eye diagram. And also there are, you see many buttons, and actually the very costly oscilloscopes has many more buttons. And if you push some button, you see so-called two-dimensional eye diagram, and which is not covered in our course. But there are, as I say, there are different definitions of eye diagram too. This is kind of one-dimensional eye diagram, and you may have two-dimensional eye diagrams. Now let's see. Suppose you are your friend in the left side building says that, hey, for my senior design project, I'm developing a new type of HDMI protocol, and here is my eye diagram. And your friend shows you this one. And this is, of course, the received signal and applied to the oscilloscope, and your sweep rate is properly already selected. Now, where is the proper sampling instant? Where? So multiple choice, 1, 2, 3, 4, 5. So where do you need to sample? What do you guess? 1, 2, 3, 4, 5. Actually, you have two answers properly, 2 and 4. If this signal has this one in +1 and -1. See that? If you sample at this, your signal could be one of these samples, near +1, and here near -1, and again near +1, near -1. What if you sample here, or here, or here? Suddenly you have some sample near to 0, which is far from these things, right? So in this way, we can formulate a lot of different problems, but anyway, so definitely your signal, received signal, is not a Nyquist pulse, right? Because you observe some effect of intersymbol interference, even though you sample properly, right? Mathematically speaking, a Nyquist pulse must give you a single point here and single point here. After proper scaling, exact +1 and exact -1. Of course, after scaling. Got it? So here goes some NRG signals. And again, we have bipolar, right? Bipolar. So our desired symbol is either 1 or -1. Now, what would be the proper sampling offset relative to this time origin 0? 20 some, there is no unit, let's say microsecond, for example, then your proper sampling offset must be 20 microsecond, right? Or 20 microsecond plus some offset. Now, what is the symbol rate? Symbol rate must be around here to where? So you need to measure the time interval, which is around what? 50 microsecond. Yeah, if it is microsecond, this is 15 microsecond. So your symbol rate is 50 microsecond, and your offset may be some integer multiple of 50 microsecond plus 20 microsecond, because you have this appears at 20. Got it? And how can we resolve this n? That is the topic of next section, which is synchronization. Okay, but I'm not talk about that right now. What about in this figure? What is the symbol rate and what is the proper sampling offset? And again, you have to find out some place. The problem is that, hey, it seems that here there is no ISI, right? Again, here. So if you just want to remove ISI, this time instant and that instance may be the optimal sampling instance, right? In terms of zero ISI. Right? By the way, here, do we have zero ISI? No, we have these lines, right? So, of course, here in the first figure, you have to define the optimality of your sampling instance. But just everybody may agree that this would be a good point. That's what I'm saying. But here, in terms of zero ISI, definitely these time instances are proper sampling instance. Right? What about next one? What about next one? It's very confusing, but in terms of zero ISI, maybe you want to sample here. Am I right? Just a second. And here. And here. Yeah. See that? Even though at this time instant your signal is greater, however, you may have some effect from your ISI. The problem is that if this is almost straight line, actually, this sampling rates may be better than that one, because anyway, if you sample here, you get a larger signal than this signal with some probability. So defining an optimal sampling instance is not unique. Okay? It depends on your optimality criteria. Anyway, so you can use this eye diagram to find whether your signal is good or not. If your eye diagram looks like this, there is a lot of room to improve, modify, improve your pulse shapes, or reduce some non-ideality in some filters, something like that. Got it? I remember I already talked about signal analyzer, which is a kind of combination of oscilloscope and spectrum analyzer. Long ago, we had oscilloscope, spectrum analyzer, and vector signal analyzer in a separate box. However, these days, some people combine spectrum analyzer and vector signal analyzer and say signal analyzer. Some people say that they combine oscilloscope, vector signal analyzer, spectrum analyzer all together and call signal analyzer. So we may use signal analyzer also to generate an eye diagram. Now, here goes the topic I will briefly talk. So suppose I'm saying what? Yeah, I'm saying Gabon. Then what is my message periodically transmitted? Is it Bangé or Gabon? We don't know, right? So not only this periodic signal, but also when we transmit, for example, a sequence of -1 or +1, if we transmit a lot and we don't know what is the starting point, even though signal to noise ratio is very, very high, we may not properly recover our message. So this kind of synchronization between transmitter or receiver, sometimes between receiver and received signal, must be done in digital communications. And see that again here? Which one is the first symbol? It depends on the delay introduced by the channel, right? We never know, just observing the signal. So usually in digital communications, we put some markers, some short known vector of symbols in front of a packet or a frame or word, something like that. So there are different types of synchronization. By the way, sometimes Z is replaced by S. If you're an Australian, usually they use S. But anyway, so there are different levels of synchronization. In radio communication, you also need sometimes carrier frequency recovery. That is also called synchronization by some people. Sometimes phase recovery for coherent demodulation is also called synchronization by some people. And timing of each symbol, exact sampling offset, is also called synchronization. Sometimes if you have many bits put together, then this timing is called recovered if we have, for example, slot synchronization, sometimes frame synchronization. This terminology depends on different standards. Sometimes we have to recover symbol timing. Then we find symbol synchronization, bit synchronization, then symbol synchronization, then word. Sometimes we proceed this way. Sometimes we find the frame synchronization first, and then does bit synchronization, something like that, depending on our modulation scheme. And even if modulation scheme is fixed, sometimes our order of different synchronizations depends on the signal to noise ratio. For example, in direct sequence space spectrum, which is usually designed to have low probability of intercept by enemy or unwanted receivers, the signal is very weak. In that case, if you want to try directly recover the carrier frequency or phase, your synchronization whole procedure fails. Sometimes we find some frame synchronization or symbol synchronization first, and then proceed to synchronize the carrier phase, or even sometimes after that we remove the carrier frequency offset, something like that. So never forget, the reason why I talk about this is that when I was a graduate student, I worked with Raytheon, the American company, very big, and they do design missiles, helicopters, and those things with anti-jamming capability. The problem is that my advisor had the research project with Raytheon, and my senior lab mate developed some algorithm and provided it to Raytheon. And they say that it does not work and resolve the problem. And the problem is that my senior already graduated and gone to become a professor in University of Florida. So I had to do the project. And I read the lines of their code and found that given the weak, very low signal to noise ratio, the Raytheon engineers was trying to recover the carrier frequency first by using squaring loop. And it didn't work, of course, because the signal is from the design for very weak SNR environment. So receive signal is very weak, which means the noise is very high, but you want to recover the carrier frequency first by squaring it. What did happen? Noise is squared, which is very large, so it didn't work. So I modified the algorithm so that we recover the timing first, and then it worked very, very good. Got it? So never forget. There are many levels of synchronizations for digital communication, but the order should not be misunderstood as unique. Sometimes you have to do some synchronization first and then the others, depending on the channel environment. Got it? That is my message. And if you take the digital communications course next semester, Professor John Joseph will talk a lot about this topic, very, very in detail. Okay, so yeah, I have to talk about this one next week. Okay, that's all for today.